Good morning, everyone. We'll get started here this morning. So today's problems are coming from a chapter 7 to 9 review packet that are in the lecture slides module. So if you want to follow along, we're starting, I think, on the third problem here today. We'll see how far we get. We might actually get through a lot of these problems here today. And if we do, well, I'll find some other problems to review for Monday. But for this first question, we're asked to find the total number of sigma and pi bonds for the molecule below with the Lewis structure shown. And so for the sigma count, it's single bonds or a sigma bond. So we can certainly count 1, 2, 3, 4, 5, 6 sigmas at least. But then the double bonds are a sigma and a pi. And so, and I also have to be a little careful that my lines I just drew don't confuse me into double counting some bonds. So this double bond here is a sigma and a pi. And then the triple bond is a sigma plus 2 pi bonds. So the idea would be that we could also assign like hybridizations of the different atoms. Maybe we'll talk about that after we answer the question. But when we start thinking of like a triple bond, that we have some sort of sigma bond between the C and the end, and then we have the 2 pi bonds. And so the pi bonds are the p orbitals overlapping like this, so that's one of the pi's. And then the other pi sticking like straight out of the page looking just like that pi bond. And so triple bonds are sigma and 2 pi's. Double bonds are a sigma and a pi. And so that should give us a total of 1, 2, 3, 4 pi bonds, and then a total of 9 sigma bonds. And let me erase and kind of recount just to make sure that we're on the same page here. So we should have, let me go to the pointer, so I should have 1, 2, 3, 4, 5, 6, 7, 8, 9 sigmas. So each of the bonds is at least a sigma, and then 1, 2, 3, 4 pi bonds. To make sure we get that count right. Now let's talk hybridizations, or let's deal with a second type question you might see on this type of topic. That's getting at the hybridization of the atoms within the molecule. Usually you talk about the hybridizations of the central atoms. So for example, this oxygen here has 4 total domains. It has 2 bonding, 2 non-bonding domains. And so from the 4 domains, you'd expect the oxygen to be tetrahedral. Because it's tetrahedral, that links up to being sp3 hybridized. So we're going to need all 4 of the orbitals on oxygen to hybridize to make 4 hybrid orbitals for the 4 domains. And so we have sp3 for our first O. And then we have a bunch of carbons here that are sp2. Now sp2 is the hybridization adopted by atoms that have 3 domains. So 3 total domains. So these are all 3 bonding domains, but it could be 2 bonding domains and a non-bonding domain. But these are trigonal planar. So sp2 is just the bonding model for trigonal planar molecules so that we can see orbital overlap between the bonds. So if we were asked, for example, to describe this bond here, if we said, well, what is comprising this bond? We'd probably say that it's the sp2 orbital of carbon and then the 1s of the hydrogen overlapping with each other. So that bond there would be sp2 1s overlap. We could be asked to describe this bond here. We could be asked to describe maybe the sigma bond and the pi bond. And so the sigma bond can be described by the sp2 overlap, because both the carbons on either side are sp2 hybridized. So the sigma bond is from the sp2 overlap. And that's because each of the atoms would have a hybrid orbital pointing right at the other. And so a bond made about the internuclear axis of the atoms is a sigma bond. And then what about the pi bond for that double bond? Well, the pi would be the leftover, the unhybridized p orbitals. A little hard to sketch maybe. I don't know what color works, but I just want orbitals sticking straight out of the carbon atoms, p orbitals overlapping in a plane. And so this would be 2p overlap, or unhybridized. So the p orbitals that weren't hybridized with the sp2 set. So we could then look at the carbon and nitrogen here and say that they're sp hybridized because both of those are linear. So linear domain goes sp, we only need 2 orbitals, so we have carbon sp2 hybrid orbitals, nitrogen sp2 hybrid orbitals, so the sigma bonds, the sp-sp overlap, and then the pi bonds would be the unhybridized p orbitals overlapping. Okay, let me erase one more time, because there's a lot of questions you can ask on a structure like this. Another one would be like bond angles. Can you predict some of the bond angles? I think we can predict most of the bond angles here. Like for example, this bond angle here has to be perfectly 180 degrees. There's no way around it. If you have 2 total domains, the bond angle has to be perfectly 180. These bond angles here, trigonal planar, bless you, have to be 120 degrees. We can even probably make a slight prediction that double bonds repel singles a little more, so that the bond angle about the double bonds probably a little greater than 120. The bond angle for the single bonds probably a little less than 120. Some bonds we can make this comparison. Like for example, here's sp3 tetrahedral. This should be close to 109.5 degrees. Let me rewrite that. But then because the lone pairs are closer to the oxygen, they repel each other more, so this is probably a little less than 109.5. Like for example, we saw the water bond angle, which would be 109.5 if it were perfect tetrahedrals, like 104. So this bond angle here would probably be like 104, 105 degrees, something like that. So pretty close to 109.5, but not exactly. Bond angles about the other sp2 atoms, 120 degrees. And so we can predict approximate bond angles. We can even then maybe anticipate when the bond angles are a little bit off of their perfect angle. Okay, so let's move off this question on to the next one. So this goes back to chapter 7. All of these questions will be like the real exam, kind of go in and out of the chapter 7 through 9. When we're ranking size of ions, we have to think maybe how many electrons do they have? Like so sodium plus, 10 electrons, F minus, 10 electrons. Both of these atoms share having 10 total electrons. And so whenever atoms have the same number of electrons, we have to then look at their number of protons. And so we have 11 protons for sodium, only 9 for fluorine, of course in the periodic table. So we have more positive particles to pull the electrons in for sodium. So sodium is going to pull those electrons in more closely. So sodium plus is going to be smaller than F minus. And now this goes backwards to the atomic trend. Like if we said compare the size of sodium and fluorine just with neutral charges, this kind of comes back to the idea that sodium plus is smaller than sodium, 0, sodium uncharged, and then if we add an electron to fluorine, that it goes bigger than F. So anions are bigger than their neutral counterparts because you're adding negative particles, increases repulsion. And then if you're taking electrons away, I think it's really obvious that the size would decrease because you're losing the valence shell electron. Of course, sodium plus is going to be a lot smaller than sodium 0. And so if you're comparing the atom sizes when they're uncharged, this is where you just look at atomic trends. This is where sodium ends up being bigger than fluorine because sodium is bigger than an atom in common with fluorine, say lithium. So sodium's further down than lithium. Lithium's further to the left, so lithium has to be a lot bigger than fluorine. So uncharged, we're using left to right trends, top to bottom trends. So uncharged, we use atomic trends. And then whenever we have the ions that share the same electron counts, we're looking at the protons. 11 verse 9, sodium plus going smaller. And then sulfide versus chloride, also sharing the same electron count. This time it's 18 electrons. Chlorine uncharged has 17, so Cl minus has 18. Sulfur uncharged is 16, add 2 electrons, it also has 18 electrons. And so 16 versus 17 electrons, 16 versus 17 protons, more positive particles to pull the 18 electrons in, so chloride goes smaller. So we have sodium plus and Cl minus as the smaller ions in these pairs. And again, this trend here, I guess it's the same trend. If you went sulfur versus chlorine uncharged, you're just using the left to right trend. That sulfur should be bigger because size is decreasing from left to right. Some of these questions are from old exams that were kind of trickier questions, and I feel like sometimes every exam has a question or two that's on the trickier side. This was one from a couple years ago, actually autumn 18, this is quite a while ago. But what this is showing us is the a carbon-carbon single bond, kind of a like an energy diagram for two carbon atoms being brought together from far separation. Bring the atoms together, they reach some ideal bond distance, and then if you keep pushing the atoms close together, the energy starts to go back up. So every bond has its ideal distance, like we saw for hydrogen coming together, about 0.74 angstrom, I think, not that you have to have that memorized, but if you go closer than 0.74, the energy starts to go back up. And the energy here starts to go up because you have nuclear repulsion, so the nuclei of the two atoms repel each other. You also have electron-electron repulsions. And then you have the ideal distance where you have the sort of best way that the electrons from each of the carbons are most attracted to the other nuclei, and then you reduce the repulsions from not bringing them too close together. And so what this question is asking is, well, what would it look like if you kind of overlaid the carbon-carbon single bond with the carbon-carbon double bond picture? Like, so the carbon-carbon double bond versus the single bond, what you're going to think for the double bond being the solid line, the double bond's stronger. And so what it would mean for a bond to be stronger would be that the distance that the bond drops is greater. So like if you're thinking from here up to here, the stronger the bond, the lower that potential well goes. And so if we're looking at our carbon-carbon single, the double should definitely drop down lower because it's a stronger bond, because we now have 4 bonding electrons instead of 2. And then is the carbon-carbon double bond shorter or longer than the single bond? It's of course shorter as well. And so then the ideal bond distance should shrink and should move to the left. And so it should look like this picture here, where we have a stronger bond, deeper potential well, and then it's shifted to the left to show that the carbon-carbon double bond has a shorter bond distance than the carbon-carbon single bond. So, peculiar question, probably not one I'd necessarily anticipate on seeing again, but just one that kind of gets us into thinking in terms of a diagram what it looks like to have a stronger bond, so it's like a deeper potential well. So if you're thinking of just the bond coming together and forming, stronger bond goes lower, and then if it's shorter, the bond distance would shrink as well. So if we're describing the bond, so Valen's bond theory is the one that talks about like hybridization of orbitals. It's the one that talks about overlapping of orbitals. Molecular orbital theory is a different theory. That's when we're drawing and sketching diagrams or using diagrams. So this question here is asking us to think about CF4. If we were sketching CF4 in terms of a Lewis structure, we'd have 4 fluorines, all of them with lone pairs. No lone pairs on carbon. We'd have 4 plus 4 times 7 valence electrons for 32. We have 8 electrons around each fluorine, so no electrons left over for lone pairs. Just to make sure we see how we get a Lewis structure where we have 4 bonding domains, no non-bonding domains for carbon. So we're fitting into tetrahedral molecular geometry, tetrahedral electron domain geometry, and then tetrahedral, even with 4 bonding domains, even if you had NF3 with a lone pair where we have 3 bonding domains, 1 non-bonding domain, as long as you have 4 total domains, we're tetrahedral. And then tetrahedral is sp3 hybridization. And so our hybridization of carbon here is we have sp3 orbitals pointing in the direction of a tetrahedron. And then fluorine's biggest orbital is a 2p. So we have 2p sp3 overlap. So sp3 for the carbon, 2p for the fluorine atoms. Now, there's one thing that you might be wondering, that would be, well, fluorine does have these 4 domains. Why don't we call fluorine sp3 hybridized? And I suppose we could. Like if one of the answer choices was sp3, sp3, that might be a good choice. But if you notice, there's no choice that has sp3, sp3. So you might be looking at fluorine saying, 2p versus, or are we going to call it sp3? A lot of times you have a single atom, you can just think the largest orbital, you can get overlap. And hybridization is how you can get overlap when you don't naturally get it with the orbitals on the atom. Like for example, carbon has 90-degree p orbitals, and we have fluorines at 1 and 9.5 degree bond angles. So we don't get natural overlap with our ordinary orbitals of carbon, so we have to hybridize them within valence bond theory to obtain overlap Like, we don't have to hybridize fluorine to get overlap. We can picture this overlap here with just the 2p orbital. So let me erase a little bit here. So if we just go back to having lone pairs, if we think of just what a 2p orbital could look like on fluorine, will just be like an ordinary orbital, and then we get overlap here. And so valence bond theory is just orbitals overlapping are what leads to bond formation. So orbitals overlap, we get a bond. So we call it sp3 2p overlap. If this were like CCl4, then chlorine's largest orbital would be a 3p, so we'd have sp3 3p overlap. If you had like CH4, we'd have sp3 and then like 1s overlap from the hydrogen to make our bond. So you're just kind of looking at the given atom, chlorine versus fluorine versus hydrogen. What's its largest orbital that's going to overlap with those hybrid orbitals? So sp3 doesn't really tell us anything in addition that we didn't already know. You know, for example, these bond angles are still 109.5 degrees. So we're still obtaining the same bond angle predictions that we had off tetrahedral. So when we're asked about cation configurations, this has, goes into the topic of, on what order are electrons removed from atoms. And so we might think, for, this question, we might want to go back and start from our uncharged atoms so that we can get to the right configuration for our cations. And so for like iron neutral, this would be argon 4s2, 3d6. It's the sixth atom across. Chromium is one of those weird ones where we'd expect it to be a 4s2, 3d4. And if you recall, you could also have written it 4s1, 3d5 is its anomalous configuration. It's going to turn out that you don't really need to know about that anomaly, that we're going to get the right answer here for chromium 3+'s configuration without knowing this detail here. Manganese is an argon 4s2, and it's the fifth transition metal across, so it's a 3d5. And then cobalt is the seventh across, so neutral, cobalt 4s2, 3d7. So now for cations, the rule for cation configurations is you remove the largest electrons first. And so what that means is we remove them from the highest N with the highest L value. Because N relates to size, so having a larger N value means the orbital is larger. And then the larger the L value, so a d orbital is bigger than a p orbital is bigger than an s orbital in the same shell. So if we're comparing a 4d with the 4p with the 4s, the 4d is bigger. If we're comparing a 4p with the 4s, the 4p is bigger. So this would be, like a 4d is bigger than a 4p is bigger than a 4s. Okay, so the largest orbital here is the one with the highest N overall. So the largest orbitals here are these 4s orbitals. And so the first electrons removed to make our cations have to be those 4s electrons. So for iron 2+, we lose the 4s. So iron 2+'s configuration would be an argon 3d6. And now if we ask for the unpaired electrons, that just kind of make sure that we get the right configuration. It's just one way of asking for the configuration without directly asking for the configuration. So to get the right number of unpaired electrons here, we do 5 electrons spin paired and pair up the 6th. So we have 4 unpaired electrons. And so that's not going to be the answer to the question, but you see if we removed 2 of the d electrons, well, I guess we still would have 4 unpaired electrons, but for some of the configurations, we'd come up with a different count of unpaired electrons. For example, chromium 3+, let's remove them from the expected configuration. So I remove 2 from the 4s, then I have to go to the next largest orbital, which is the 3d. Because the next largest orbitals I would have are the 3s, the 3p, the 3d, of which the 3d are the biggest. So then I take 1 away from the 3d. So for chromium 3+, the configuration would be argon 3d3. Now, if I started instead from the anomalous configuration, if I knew this anomaly, I'm taking 1 from here and then 2 from here. So I get to the same 3d3 configuration. But the key is I have to remove the largest 4s electrons first. So 3d3, of course, would have 3 unpaired electrons. You can probably see that manganese is going to be the answer. We lose the 4s electrons, so manganese 2 plus configuration ends up being a 3d5. So all those electrons spin unpaired. Cobalt is the one you might think would be 5 if you did the rule wrong. If you remove the electrons in the order we kind of put them in, you're taking them out of the D subshell first, but we don't do that. We take from the S subshell first. So cobalt 2 plus would be an argon 3d7. And this isn't like an anomaly. This is just the rule for cation configurations. And so, of course, that would have 3 unpaired electrons. We've introduced the term paramagnetic. So all these cations would be paramagnetic. They'd all be pulled into a magnetic field. If we had all spin paired electrons, a molecule would be called, or an atom would be called diamagnetic. Let's just double check to make sure we can get the configuration right for like a p block element. So let's maybe look at tin, element number 50. And so for tin, let's do tin 2 plus. So for tin 0, we'd have a krypton configuration for 36 of the electrons. And then we're in a 5s2. We're filling into the 4d10 next. And then 5p2. One thing I like to come back to is that these are the 4 valence electrons. So those are the outermost electrons. We weren't even counting the d subshell towards our valence count, if you recall. So if you're expecting which electrons are we going to lose first, probably these, because they're the largest. So for tin 2 plus, we go to krypton, 5s2, 4d10. And then if I have to go to the configuration for tin 4 plus, to go to another cation that's common for tin, then we're taking the next 2 valence electrons. So we're taking the s electrons next, the next largest orbital. So this would be a krypton 4d10. And so I think you can maybe even appreciate then why we're not counting the 4d10 toward the valence count, because we're not even removing them. And tin like 6 plus isn't even like a normal cation. Tin 4 plus is the highest charged common cation of tin. Okay, so for cation configurations out of chapter 7, what we're doing here is making sure to remove the electrons from the largest orbitals first. If you go back to the idea of attraction to the nucleus, the furthest electron away is the one that's least attracted to the nucleus. Another way of saying that is it experiences the lowest effective charge. So the reason why these s electrons are being removed first is because they experience the lowest effective nuclear charge. So the charge they're experiencing off the nucleus has been blocked and shielded by the other electrons that are closer to the nucleus. And so another way sometimes these questions are worded you'll see is like which electrons in a particular atom experience the highest versus lowest effective charge. The 1s electrons are always the electrons experiencing the highest charge. They're the ones that are seeing the full charge of the nucleus, and the largest orbitals are the ones that are experiencing the lowest effective charge. And so for like tin 0, for example, like it's this orbital here that experiences the lowest z effective, and then the next one would be the next lowest effective charge would be the 5s, then the 4d, etc. So lattice energy, let's talk about that a little bit. So for like MgO, for example, its lattice energy would be the energy associated with the solid ionic compound dissociating into its ions in their in gaseous state form. So it really gives you a measure of how attracted the 2 plus and the 2 minus ions are together in the ionic solid, where it's Mg2 plus, O2 minus, Mg2 plus, O2 minus throughout an extended 3-dimensional structure. So you're just getting a measure of the ionic bond strength for the Mg and the O and MgO. Now, if you're comparing this lattice energy for MgO 2 plus 2 minus with calcium sulfide, which is also a 2 plus 2 minus, what you want to compare would be the relative size of the ions. That calcium's bigger than magnesium, and then sulfide's bigger than oxide. And so calcium sulfide, the ions are further away from each other, which means they're going to experience a lower attractive force relative to each other. So the kappa Q1, Q2 divided by D equation relating to the energy of electrostatic attraction or repulsion. And again, with plus and minus, or minus and plus, you get the energy goes down, you get attraction. So we might think about the magnitude of the energy of attraction between plus and minus charged ions, so that you can imagine if we put the ions further away from each other, divide by a bigger number, that we reduce the energy of electrostatic attraction. So further away, lower attractive forces. And the reason why I like to think of the magnitude here is because the energy attractive force becomes like less negative. And so I want to think about the magnitude of that value becoming less negative. So further away, ions further away, less attracted together. So think about having a plus 2, minus 2, like 2 miles away from each other. There's like no attraction there. If they're like right on top of each other, much stronger attractive force. So smaller gives us a stronger ionic bond. So the greater lattice energy would be for MgO in group 1. And in group 2, we're comparing 2 plus 2 minus with plus minuses. And of course, higher magnitudes of charge. If we increase the magnitudes of charge here, we're going to increase the magnitude of the energy of attractive forces. So having greater charged ions gives us a greater lattice energy. So MgO and MgS would be our answers here. So electron affinity of fluorine is, we're told here, is minus 328 kJs per mole. Which statement is true? Well, let's first think about what electron affinity means. The energy here is for this reaction. It's fluorine absorbing an electron to go to F minus. This is our electron affinity reaction. So it's the electron being absorbed by the atom. And so when you're told this reaction is minus 328 kJs, it means fluorine absorbing an electron to form F minus has an energy that's exothermic, energy is given off by this reaction of 328 kJs per mole. And so when a mole of fluorine gains an electron, 328 kilojoules of energy is released. I think that's exactly what I was just saying. And if we can then read the other statements on why they're wrong. So when a mole of F loses an electron, 328 kilojoules is released. That would be like ionization energy. So ionization energies are atoms losing electrons. So this is a statement that would go along with a value that might have been an ionization energy given to us. Ionization energy for all neutral atoms are positive, meaning energy is required for an atom to take an electron, break it off the nucleus, the positive charge holding it into place. So for neutral atoms, energy is always required for ionization, so energy has to be absorbed for all atoms to lose electrons. When a mole of F gains an electron, 328 kilojoules is absorbed. Well, that would be true if this were plus 328 kJs per mole, but energy is being released here by the absorption of the electron. And then, again, not ionization, but we're gaining electrons here. One interesting thing is if you take this reaction in reverse, of course, from chapter, I don't know what it was now, chapter 5, we can flip a reaction. You flip the sign of the delta H. So the delta E or delta H of this reaction would be plus 328 kJs if we flip this reaction, so it turns into an endothermic reaction. You see what that kind of means is that the electron that we absorbed into fluorine now has a built-in attraction because it takes energy now to remove it once it's attached to the fluorine atom. So it takes energy to remove an electron from F minus, just kind of showing you that the electron that was absorbed into the fluorine atom now takes energy to remove it. So in the what is the formal charge of phosphorus in the Lewis structure of phosphate ion in which all atoms obey the octet rule? Okay, so let's count up our electrons. And this could very well be one that you know it right off the bat. Like some of you guys, and certainly I know it too, but you may already know the Lewis structure. If you're that savvy with Lewis structures that you have it memorized through doing enough examples, that's fine if you don't have to do these rules every time. But if we have to get a Lewis structure right, I just always revert to the rules just to make sure that I'm starting with single bonds, I'm attaching them, I'm completing the octets of the non-central atoms first, I'm counting the available versus the used electrons, making sure I distribute the proper count. And this is all 32 electrons with none left over. And so then phosphorus here has a positive formal charge. The oxygens are all minus. If we're not sure on these charges, phosphorus should have 5 electrons for a neutral charge, and it only has 1, 2, 3, 4 electrons closest to it, because we're just imagining we break the bonds in half to calculate our formal charge. So formal charge of phosphorus plus 1. And for the oxygen formal charges, they should have 6. So you look at the valence count for the atom. So oxygen has 6 valence electrons. If it did, it would have a neutral charge. Each of the oxygens have 1, 2, 3, 4, 5, 6, 7 electrons closest to them for minus 1. We should be able to take all these formal charges and sum them up. So minus 1 times 4 plus 1 equals minus 3. So we should be able to get the overall charge of the molecular ion through adding up all the individual formal charges, just like adding up all the oxidation numbers in chapter 4. So we have here phosphorus satisfying the octet rule. Now the octet rule is all the atoms counting all the electrons in the bond surrounding an atom. So for phosphorus, we have 8 electrons surrounding the atom. And so this here would be the best Lewis structure. Well, it would be the Lewis structure for phosphate that satisfies the octet rule for all atoms. And then the formal charge of phosphorus would be plus 1. Now, there is a second Lewis structure we can sketch that minimizes magnitudes of formal charge, sometimes called the formal charge rule, Lewis structure. And so if we make a double bond with one of the structures, so we kind of move in, make a double bond here with one of the O's, and then we have to then somehow imagine resonance taking place. So here we end up with phosphorus with a 0 formal charge, oxygen with a 0, then this would resonate through the structure, so we'd have resonance taking place. So we'd still have 4 equivalent PO bonds, all the same length around the molecule, no matter which Lewis structure you're thinking here. And then we end up with 4 different Lewis structures we could sketch for the phosphate that minimizes the magnitudes of formal charge. If this question said, what's the formal charge of phosphorus in the Lewis structure that minimizes magnitudes of formal charge, we would say 0. So probably the better Lewis structure is the one that satisfies the octet rule. It's kind of hard to imagine how an atom like phosphorus can expand its octet. It's hard to imagine if you think of sigma and pi bonding the way we've talked about it. If you want a double bond to be a sigma and a pi, there should be leftover p orbitals, where phosphorus here having 4 domains would put it in sp3 hybridization, meaning no p orbitals are left over on phosphorus for pi bonding. So I don't know how we make those bonds. I don't know how we picture the resonance, any of those details. So this Lewis structure here, probably the better one, but it's also the one that just answers the particular question. So the pi bond between 2 carbon atoms in ethylene forms between overlap of what type of orbitals. And so we might need a Lewis structure. It's C2H4, it's blurry. So we have 2 carbon atoms, 4 hydrogens. In terms of our count, we have 4 times 2 plus 4 times 1. So that's 8 plus 4, that's 12 total electrons. I have 2, 4, 6, 8, 12, so 2, 4, 6, 8, 10 so far, if I count correctly. And so then I make a double bond that uses up the total electrons we have available and then gives each carbon an octet. So each carbon has 8 electrons surrounding it. And then also 0 formal charges. So the formal charge of carbon, 4 minus 4 for 0. And so we have a double bond between our 2 carbons. Let me resketch. And so I can describe all these bonds here. Like I could describe this bond here as being 1s sp2 overlap, because the carbon atoms being trigonal planar or sp2 hybridized. And so I can describe the sigma bond here as being sp2 overlap. But then the pi bond would be described by the unhybridized p orbital. So I have this unhybridized p orbital. Again, hard to sketch, but it's one sticking straight out of the page. Sometimes a way you can sketch this a little bit more easily is if you just try to use like 3 dimensions. If you try to use the carbon hydrogens coming at us and going away from us with wedges this way, then our p orbital would be in the plane of our paper, a little bit easier to sketch. So if you just imagine the hydrogen sticking in this plane here, and then you can imagine the p orbitals overlapping to make our pi bond. So that's our pi bond, and it's coming from two p orbitals overlapping with each other. The sp2 orbitals overlap, but those make the sigma. So this is our sigma bond between the carbon atoms. And then a 2p and an sp2 hybridized orbital is just kind of nonsense. So this is just not a sensible orbital. So 2p orbitals overlapping make the pi bond. The sp2 overlap make the sigma. So we haven't talked, I guess, at all about some more just identifying electron domain geometries for molecules. This usually goes back to like a Lewis structure. And so if we have central phosphorus, 5, 3 times 6 plus 3. So that's 26 total electrons. We have a central phosphorus, 3 oxygens. When I do a Lewis structure, I may not think too much about the geometry, so I might just be trying to make sure I get all the atoms put into place. And then count my electrons used. That's 24 electrons, 3 times 8. So 2 electrons left over onto the central atom. And so this is actually a Lewis structure here that I don't need to make any double bonds. I mean, this is the best Lewis structure. I have a 0 formal charge on phosphorus, negatives on the O's, single bonds all the way around. And so now I have 4 total domains. So the electron domain geometry should be tetrahedral. So I'd have a central phosphorus with a tetrahedral structure. And then I might have this as my picture, and then I'm just going to put a lone pair into one of the spots of the tetrahedron. And then my oxygens on the other spots. So the electron domain geometry, tetrahedral, and then the molecular geometry is the name of this shape here, which is a pyramidal trigonal shape. So it's a trigonal pyramidal geometry. So make sure for the, my recommendation is for the shape name, make sure it makes sense, because it's just, you're trying to name the shape of the atoms. So you're just trying to say, forget about the lone pair in terms of the shape. I mean, they give the molecule its shape, so don't forget about the electron pair totally. But when you're giving the shape, you're just naming the shape that the atoms have. Sometimes I would call it like an atom geometry, so it's just a geometry of the atoms. Even though it does depend on the total electron domain geometry, it's just the geometry of the nuclei, so we're just trying to name that shape. And so when we have linear, that's the only so if you have 2 domains, they have to be bonding. If you had a bonding domain and lone pairs, and that's just like a diatomic molecule. So a linear molecule like CO2, for having 2 domains, has to be 180. We have trigonal planar, where you can have all 3 domains bonding 120-degree bond angles, or you can have something with a lone pair. So if you just start to go through kind of the permutations, like we can put a lone pair on one of these spots, and then we still have a trigonal planar geometry. You can have tetrahedral with 1 lone pair or 2 lone pairs. So you go from tetrahedral to trigonal pyramidal to bent for something like water. Whenever you have 3 atoms, remember, you're really just trying to say, is the bond 180 perfectly and it's linear, or is it something bent where it's not 180 perfect? So this molecule structure here would be bent. Just kind of going through the permutations of like trigonal bipyramidal coming next. And so for trigonal bipyramidal domain geometry, looking something like this, we replace with a lone pair on the trigonal planar part. So we make a seesaw geometry. We replace a second lone pair if we have 2 lone pairs, 3 bonding domains, for like a T-shaped geometry. So we're going from a seesaw structure. And again, like sometimes the seesaw structure, we get a little confused on what we mean by that. If you just imagine picturing the structure here, you can kind of see it teeter-totters on itself, so that's why the seesaw is the name of that geometry. We have the T-shape if you add 1 more lone pair. So if you flip that structure, it looks like a T, so we have a T-shape. And then we add another on the equator if we have to replace another lone pair, and then we go back to linear. So if we have 3 electron pairs, 2 bonding domains within trigonal bipyramidal electron domain. We have either seesaw, T-shape, or linear molecular geometries. And then octahedral, square pyramidal, square planar. I can draw those pretty quickly. So we have square octahedral. So if you replace an electron pair, pick any of the spots, you end up with a square pyramid, so square pyramidal. And then replace a second lone pair on the same axis, then you end up with a square planar geometry. So which diagram looks like, so we have a potential energy diagram shown. What is it representing? So we have 2 helium atoms, we have hydrogen, 2 hydrogen atoms, and then 2 sodium atoms. And so this diagram here, it would not be representing the 2 hydrogens, because 2 hydrogens would go down relative in energy. So we'd form a stable bond between 2 hydrogen atoms. 2 heliums do not bond together. 2 sodium cations don't bond together. So I think the choices are missing here, but this could be due to the 2 heliums, or this could be due to the sodium plus sodium plus. So we get repulsion in both of these cases. So it could be either the 2 helium atoms, which don't form a stable bond together. There's no bond between 2 heliums. Likewise, 2 sodium cations just repel. The positive charges repel and would go upward. So we may not be able to identify which one this corresponds to, but it would correspond to either one or 3. And so this is just showing us that 2 atoms that form a bond, should the energy becomes negative, we go downhill relative in energy, you form that stable bond. If you can also think about every bond from like chapter 5, we saw this in chapter 8, every bond enthalpy is positive. So it takes energy to break every bond. So if you know you form a covalent bond between the 2 atoms, that has to drop in energy because energy has to be absorbed to break the bond once you make it. And so then helium atoms repel each other, again, because no bond forms. If we recall, our diagram for helium had 2 electrons for each of the helium atoms. And then so we're making a bonding orbital and an anti-bonding orbital. So we had the sigma 1s and the sigma 1s star anti-bonding orbital. And the anti-bonding orbital is even more destabilized and the bonding orbital stabilized. So 2 helium atoms do not bond together. So our bond order here was 1/2, 2 minus 2 for 0, meaning no bonds forming there. So we don't get a stable bond between 2 helium atoms. And then here's this electrostatic repulsion. So it's just plus plus repel, energy goes up. So which molecule below contains an atom that's sp hybridized? So this just kind of makes us go through the Lewis structures, but we can probably, because we've seen it, like the BeF2 is the one that's likely here, because beryllium only has 2 valence electrons, 2 times 7 for the fluorines. We only have 16 total electrons, so I have a central beryllium, fluorine atoms, and then that's our Lewis structure, because we have used all of our electrons, so none left over for beryllium. Fluorines have a 0 formal charge. Beryllium only has 2 valence electrons, so it's actually happy in terms of charge, meaning it's neutral formal charge. Atoms that have a relatively high formal charge, like if you imagine an atom with like a +5 formal charge, it's kind of crazy because that's like too high of a charge. It's going to be pulling electrons in towards itself, trying to reduce it. But being neutral is relatively happy. The nucleus of beryllium just doesn't have enough charge to pull any more electrons towards itself. So it has a 0 formal charge here. And then this would be perfectly 180 degrees, perfectly linear. And then this would be described for 2 domains as sp hybridized. So this would be our sp hybridized atom, would be BeF2. Now the others, just to make sure that we can get maybe the right Lewis structure, or maybe even on some of these we can predict. We haven't talked much about polarity in terms of molecular polarity. Like BeF2, our dipoles here would be opposing each other. The fluorine should pick up a partial negative because fluorine is really electronegative. So it should be pulling that bonding pair closer towards itself, going partial negative. But the 2 dipoles perfectly cancel out, making the molecule nonpolar. So BeF2 would be a nonpolar molecule despite having these polar bonds, because those dipoles are canceling each other out. And so nonpolar molecule here, SF2 would be 6 plus 2 times 7. So that's 20 electrons. So this is sulfur, fluorines, lone pairs, just like we did for BeF2. but only 16 electrons used, leaves 4 behind for sulfur. So we go sp3, hybridization for the sulfur atom from tetrahedral domain. And then our geometry here would be bent, not linear. This might look linear. This might look like BEF2 where you're saying the dipoles, do they cancel? Well, we have to think of the molecular geometry. So we have to think here, we're going to have a tetrahedral geometry, fluorines here, lone pairs on the other tetrahedral spot. I'm just going to sketch those here. Maybe you're picturing them in like sp3 type orbitals. Those orbitals are going to push these fluorines less than 109.5 degrees together. And so definitely not linear. And so we're going to have a negative end of our molecule on this side and a positive end on the sulfur. So SF2 would be polar. If we're going to have a molecule that's tetrahedral, that's nonpolar, we're going to need one of two things. Either the atoms to not differ in electronegativity by much, maybe like C and H don't differ by electronegativity by much, or just all the atoms are exactly the same. If we have like CF4, CCl4, CH4, those molecules have to be perfectly zero in dipole moment because we would have the same atom across this structure. So if you imagine CF4, we have the same charge on all ends of our molecule, just like for BEF2, so this molecule here would be perfectly nonpolar. So if you want a molecule to be nonpolar, you need the same atom across the structure. Like you need like the electron domain geometry to be the same as the molecular geometry. So you need tetrahedral geometry, same atom across. You need trigonal planar, same atom across, etc. PF3 would be 5 plus 3 times 7, that's 26 electrons. So this is going to be phosphorus with fluorines for 24 of those electrons. And then we're going to have 2 electrons left over for phosphorus. And so this is also going to be sp3, also going to be 109.5 degree bond angles, also a little less than 109.5 degree bond angles. Molecule would be polar. And so the last one, CH2O, we've kind of seen this one before, but 2 hydrogens and the oxygen on the central atom. If we do the lone pairs, positive formal charge on carbon, 4 plus 2 plus 6, that's 12 total electrons. So 2, 4, 6, 8, 10, 12 electrons distributed. And then let me reduce the formal charge with a double bond. Of course, we would expect 4 bonds for carbon. We get that with the double bond to O. Oxygen likes to form 2 lone pairs, 2 bonds. We get that also with a double bond. And so for, let me uncircle, I don't know why I circled that. But so for the structure here, we'd have a polar molecule. We have an sp2 center because it's trigonal planar. And then because oxygen is a different atom than H, we now have a break in that polarity. So we have a negative side on our O, a positive side on the opposite end of the molecule. So we just need one side of the molecule to have a different charge than the other. Like if I go back to my CF4 example, if I take any one of these atoms and just change it to any other atom, if I just take a fluorine and change it to a chlorine atom, then that all of a sudden becomes a polar molecule. Just because I break the charge trend. Like I want the exact same charge on each of the atoms on the outer like periphery of the molecule in order to term the molecule nonpolar. But if I break that, if I make chlorine just because it's not as electronegative, we get a different charge on chlorine than the other end, then we have a polar molecule. One way I like to think of it is if you put a positive charge around a polar molecule, then the most negative end goes towards a positive charge and like wins that fight. If we go back to having this just be a fluorine atom and think about what happens there, if we put a positive charge near CF4, then all those fluorines just fight for the charge. Neither one of them can win because the molecule will just spin and all the atoms kind of fighting over the positive charge. So we need like a net charge on the molecule or like a net pull on the molecule in order to term it polar. So again, CF4 nonpolar, like change one of the atoms to anything else, then we would have a polar molecule. This is kind of getting at what we were talking about earlier. It's the same molecule as the first example of the day. So the number of sp2 hybridized carbon atoms, we'd just be looking at carbon here, carbon here, carbon here, sp2 hybridized. And so we'd have 3 sp2 carbons, sp here. Now, the outer atoms, like this, you could call sp2, but just not a carbon atom. So you might call that O sp2. You could call this N sp hybridized. In terms of their hybridization, this O here, sp3. So we have 3 sp2 hybridized carbon atoms. Among boron, carbon, nitrogen, oxygen, which atom, when bonded to fluorine, forms the most polar bond? So, of course, being further away means boron has the lowest electronegativity, fluorine has the highest, so we get the greatest difference with the BF bond. So, pretty easy question here, I think, in terms of the BF bond being the more polar of the bonds, CF next, NO, and then OF being the least polar of these possible choices. And of course, the least polar bond of all would be the F2 bond. So this molecule here would be perfectly nonpolar. So 0 formal charges all the way around. And then if we say, well, what are the actual charges on fluorine in this molecule? They're actually 0. If you then said, well, what about like HF? The formal charges are, well, why did I do that? That's funny. This would be 0 for our formal charges, but then the bond pairs not being equally shared, fluorine's more electronegative than H. We pick up a partial negative and a partial positive. The partial charges are representing more like the real charges you expect in an actual molecule. Like if you encounter a molecule of HF, you'd really expect the fluorines to pick up a negative charge, the hydrogens, the positive charge. The formal charge is just a way to help us with Lewis structures. It's a way of trying to assign charge if the bonds are being equally shared, and then we can break that assumption and let the bonds kind of fight in the more electronegative atoms win the electron pairs and adjust charge accordingly. So back to a size question again. So like calcium versus chlorine. So calcium and chlorine, not in the same row, but they share magnesium in common. So this calcium would be bigger than magnesium. Magnesium's bigger than chlorine being in the same row. Size is decreasing left to right. Size increases though top to bottom. So calcium has to be bigger. So chlorine is smaller than calcium. And then scandium 3+. Scandium has 21 electrons. Take 3 away, has 18. And then sulfide has 18 electrons as well. More positive charge for scandium to pull those electrons in because we have 21 protons versus 16. So scandium is actually going to be quite a bit smaller than sulfide ion. So we go scandium and chlorine. So now this does use the word photoelectric effect, but remember the photoelectric effect would be like a photon causing the electron to be ejected. So one photon causing the ejection of one electron. Does the first or second electron of sodium or magnesium require a photon of the greatest energy to be ionized? And so in some ways, like we don't even need to work photoelectric effect in here. We could just say, does the first or second ionization of sodium or magnesium require more energy? So which ionization requires most energy? So we're probably thinking it's definitely not going to be the first because the second ionizations are always higher than the first for any atom. So it should be one of the second ionizations of one of the atoms, but then which atom? And so if you're thinking sodium going to sodium plus an electron, and then sodium plus for the second ionization going to sodium 2 plus an electron, this is the step that's usually a lot higher than the first because we're removing a core electron. So core electron removal takes a lot of energy. Magnesium to magnesium plus an electron. The second ionization is just the plus going to 2 plus, where we're not yet removing a core electron. So this ionization, while higher than the first ionization, is likely not going to be higher than sodium second. Sodium second, because it's the core electron removal, is going to be a lot higher. So anytime we have a core electron removed, we get a really high ionization energy. And so we're going to get a higher second ionization energy for sodium. And this is just getting at, sometimes you look at a chart that's like, the ionization energy per electron, and then the fifth one's really high. And so for this type of question, it's like the first, second, third, fourth were valence electrons, so we have 4 valence electrons. So this would correspond to an atom with 4 valence electrons with the fifth removed requires the greatest energy. So something that looks like that. So this is just getting at that kind of topic, that once we start removing core electrons, the ionization energy jumps up to be a high energy. If you said magnesium's core electron removal, so the third of magnesium, that would certainly be a lot higher than magnesium second, because magnesium's smaller, higher charge, etc. Okay, so that we got through 18 of the 28 questions so far in the packet. We'll look at the remaining 10. I'll probably find a couple extra questions to review after those 10 on Monday. All right, guys, remember, no class Friday, Veterans Day, so enjoy the day off, and Monday exam, so good luck preparing. So have a great weekend. Guys, practice exams are posted on Carmen if you haven't seen them yet. So the practice exams are up.